Okay, now this next exercise, exercise 5.5, is how to find the area of a minus segment. Now, here in this circle here, we've got two segments. This segment here is the minus segment, and it's called a minus segment if it takes up less than half of the circle, and this here would be called the major segment. So on this diagram here, I've got a circle, radius r, angle subtended at the center is theta. I've shaded my minus segment there. So I'm going to draw a minus segment here again. And to find the area of the minus segment, which is in there, so area of minus segment is equal to, it would be the area of the sector minus, so the area of the sector is that whole thing, minus the area of the triangle. Now remember, this is r, and theta. Now, we looked at area of a sector in exercise 5.4, and the formula for the area of a sector is a half r squared theta. And the area of the triangle there, we've learned that in trigonometry in year 11, and it's a half AB sine C. So it's a half. Now, I'll just draw the triangle here. Remember, if you've got like triangle ABC there, the area of this triangle is a half of A times B times sine C. So it's doing that here. It's a half times R times sine theta. In other words, it's a half r squared theta minus a half r squared sine theta. Okay, so we can see that a half is a common factor and so is r squared. So therefore, the formula for the area of a minus segment is a half r squared theta minus sine theta. Now, when you use this formula, so this is area of minus segment. When you use this formula, theta must be in radians. You don't go and put 30 degrees here for your theta. And when we were using the formula for a half r squared theta, which was the area of a sector, remember theta was in radians, okay? So theta must be in radians for both of these. So even though area of a triangle, we've used it before with degrees, you must use it with radians. If actually, no, I think you must use it with radians. So when you would have used this formula bit in year 11, a half r squared sine theta, you may have done a half r squared sine 30. Now we know sine 30 is a half, for example. But this time, when you're entering it into your calculator, your 30 degrees won't be 30, it'll be pi on 6, okay? If that angle at the center was 30, for example. So the important thing here is that your calculator must be in radians mode. Now, it must be in radians mode because theta is in radians. So where theta is in radians. Now, you've already, so when you're doing L equals r theta for arc length and A equals a half r squared theta for area of a sector, when you are entering these into a calculator, it doesn't matter whether it is in radians mode or degrees mode, because you're not using one of the trig functions, which is sine, cos, or tan. Because you're using a trig function here in the formula A equals a half r squared theta minus sine theta, the calculator must be in radians mode because you're doing sine of an angle, okay? And whereas here, if you do L equals r theta for a particular arc length, whether you use radians mode or degrees mode, you're going to get the same answer. And same with the area formula, a half r squared theta. Whether you're in degrees mode or radians mode, you're going to get the same answer. But for minus segment, you must be in radians mode. Now just some examples from exercise 5.5. Now the first example is to find the area of the minus segment of a circle if the radius is 7 millimeters and the angle subtended is 45 degrees. Okay, so remember we're finding the area of the minus segment. Radius is 7. Angle subtended is 45 degrees. So our formula area of minor segment is half r squared theta minus sine theta, which is a half times 7 squared. Now, your angle theta is 45 degrees, but that's not radians, so it's pi on 4. So it will be pi on 4 minus sine of pi on 4, which is a half of 49, which is 49 over 2, pi on 4 minus, now you can enter it like that, but we know that that is 1 on root 2, sine pi on 4. So now you just enter this on your calculator. Actually, we want the exact area, so find the exact area of the minor segment. So now, just expanding, you would get 49 pi over 8 minus 49 over 2 root 2. Now, if we want, we can rationalize this second fraction, so times root 2 times root 2, we would get 49 pi over 8 minus, that's 49 root 2 over 2 root 2 times root 2 is 2 times 2, which is 4. And if you want, further still, you could write this as a common denominator. I'll just go up here. So that would be 49 pi minus, this would be 98 root 2 all over 8, but you can leave it like this. Or I can even go 49, so there are many ways you can leave it, okay? So that's with a single common denominator there. What we could also do is also take out 49 as a common factor here. 49 over 8, for example, pi minus 2 root 2 is another way I could write that, okay? Okay, another example, exercise 5.5, question 5. The area of the minor segment cut off by an angle of 2 pi on 9 is 500 centimeters squared. Find the radius of the circle to 1 decimal place. So we know that area of minor segment is half r squared bracket theta minus sine theta. So the area is 500. It's a half times r squared. Theta is 2 pi on 9 minus sine of 2 pi on 9. So 500 times 2, so we've got 1,000 equals r squared times this, 2 pi on 9 minus sine of 2 pi on 9. Now that is not an exact value, so we can just go r squared is 100 divided by 2 pi on 9 minus sine of 2 pi on 9. And actually just go that r is actually the square root of all of that. Be careful, you want to work this out first and then square root it, okay? Sorry, that's 1,000 there, so if you calculate that, it's 134.4 centimetres, correct to 1 decimal place. Okay, question 7. A chord 8 millimetres long is formed by an angle of 45 degrees subtended at the centre of a circle. Now this is a chord that's 8 millimetres long, it's not the arc. So they're not giving you the arc. What that there is the arc. This is the chord. A chord is a straight line on a circle joining 2 points. So that is 8 millimetres. And this angle here is 45 degrees. So remember, this is a radius and this is a radius. So the way that we're going to be able to find out this radius, we've got a non-right angle triangle. You have to think back to year 11 2-unit trigonometry. And the only way we can do this is to use the cosine rule. Okay, so all this C and this A, B and capital C, I've got C squared equals A squared plus B squared minus 2AB cos C. Okay, so we can't even use, we would not even actually. The other thing we could use is the sine rule, because we know this is an isosceles triangle because they're both equal radii. So we could use the sine rule as well. So if I want to use the sine rule, I would go 8 over sine 45 equals whatever this angle is. Now I can work out what that angle is. So I would go 180 minus 45 is 135 and divide that by 2, and that would be 67.5 degrees. So I could go r over sine 67.5 degrees equals 8 over sine 45. That's one way of doing it. Or I could use the cosine rule and go 8 squared equals r squared plus r squared. minus 2 times r times cos 45, and that actually looks like it would be a little bit more complicated. So let's use the sine rule instead. So we're going to go r over sine 67.5 degrees. You're going to, if you use degrees, you must be in degrees mode on your calculator, equals 8 over sine 45 degrees, and therefore r is 8 times sine of 67.5 degrees over sine 45 degrees. Okay, let's calculate that. So the radius is 10.4525 ... I'm just going to put 10.45. Actually, I'll just use the 45, to 2 decimal places. And now the area of the minus segment is just your minus segment formula. Area equals a half r squared theta minus sine theta. So it's a half r squared. Now theta here is not 40. We don't use 45 degrees. In this case, we must use pi on 4. Okay? Now, if you decided up here to use the sine rule in radians, you'd have to convert the 67.5 degrees and the 45 degrees to radians. It would work if you were in radians mode. But if you're going to use 45 degrees and 67.5 degrees in these formulas, you must use your calculator in degrees mode. So just be careful, please. Now, over here, we only use radians mode for minus segment. So we've got area is a half r squared, theta is pi on 4 minus sine of pi on 4, which is a half r in this. I'm going to use the non-rounded off version. A half times 10.4525 ... squared. I'm going to keep that answer in the calculator. Bracket pi on 4 minus sine pi on 4 is 1 on root 2. Now we can just enter that into the calculator. Entering that in the calculator, I get 4.2768, etc., which is 4.3. Just going to do this to 1 decimal place, if that's what they ask. 4.3 millimeters squared, because the chord cuts off and it's an 8 millimeter chord, so our units are millimeters squared for area. Just be careful if you're given a chord. Sometimes you've got to find the radius, or sometimes you've got to find the angle subtended. You may not always be given the r and the theta in these problems. Question 10 from exercise 5.5. The length of an arc is 8.9, so that's an arc. So the length of this arc is 8.9 centimeters, and the area is 24.3 centimeters squared. And you have to find the area of the minor segment. Actually, we did something similar to this in the last exercise. So remembering, you're going to have to find r and theta here and solve simultaneously to work them both out. And once you've worked out what r and theta are, then you'll be able to solve simultaneous. So just again, L is r theta, so 8.9 is r theta. Area is a half r squared theta, so 24.3 is a half r squared theta, and you can bring this 2 over, so 48.6 is r squared theta. You'll need to rearrange. You've got 2 simultaneous equations. Solve for both r and theta. Once you've worked them out, you can do the area of the minor segment. So I'm actually not going to do that. You can do that yourself.